course. They want to offer it in Professor Azbek is going to teach the power electronics one next year. The one the course we had before. He's going to teach it, but I'm going to teach another course. Power system analysis. They put it under a special topic, for those when they want, because it doesn't have a course number. And energy conversion is going to be offered under 121. They were going to offer energy conversion fall quarter, power system, winter quarter, and power electronics two. Right now, I'm going to teach those three courses. I asked them to switch. Energy conversion would be in the winter, and power system analysis. It is not going to come under that name. It's going to be a special topic. Under my name. If you are guys are interested, and next year it's going to be power system analysis. They're going to give a course number for that. Looks like they approved. They want to go with that. We have at least 4 courses now in power. Just for your information. This is one more topic, on the switching. I'm going to talk about that one on the three-phase already. We talked about that. The harmonic elimination for the three-phase inverter works or doesn't matter. Single-phase inverter. We talked about that one. I'm just going to give you the equation, for both type of switching, either bipolar or unipolar. And after that, we're going to move on to the more like a math part, control part, for a while to calculate all the equation, all the required, control things we need. For a while, we're going to be on that side. And after that, we're going to go back to the DC to DC converters and control and any question from the last class? Today, really, my energy level is really, really zero, even if worse than the last class. Let's see how much I can hang on. Harmonic elimination. What we call it harmonic reduction. Remember on the single phase inverter, we talked about this one. The only one we talked about like this. If you have a waveform like this, right? Compared to the 50%. This is, for example, you can set for third harmonic or fifth harmonic, whatever. So they call this one notch. Basically, there is look at a quarter cycle, right? We have only one notch here, right? You can control one element. You can, for example, either you can say, I can eliminate the third harmonics, or I can eliminate the fifth harmonics, or I don't know, 7 harmonics, whatever. That's it. I can do one. But if I will have a 2 notch for some reason, how I'm measuring, for example, I have something like this, right? Like this. For example, like now I have a 2 notches, right? So I can do 2 things. For example, I can eliminate third and fifth, or I can eliminate third, right? And control the one, you know what I'm saying? So because I have 2 parameters to control here. There's a 2, we'll name it here. There are 2 parameters we can control. Now let's look at here. So let's say if we have a waveform like this, in general. If we have a waveform like this, this is with 1 notch. The one I'm going to put here is with not 1 notch, but I'm going to give you a general equation. It should be symmetric. I just put this half here, but you repeat this one exactly over there. You know what I'm saying? It's going to be like this. This is a pi. If you look at it, this is this part. Now we put this part here, vice versa. It's going to be like this. this one should be equal to right. Very good. This one is equal to this one. I'm saying you have this quarter cycle, this is a 2 pi. And this is symmetric, you know. This part is symmetric, and that part is odd symmetric. You know, odd symmetric means, you know, you turn it 180 degrees also. Now, let's call this one. If this one is the alpha 1, and this one is the alpha 2, basically, as I said, this is symmetric. If we are going to mark it here, this one is going to be, this is the alpha 2. From here to here also is how much? Alpha 2. Basically, this one is going to be pi minus alpha 2, right? Or, again, this one is alpha 1, this one is alpha 1. So from here to here is how much? Because this is the pi, right? And this is the alpha 1, right? Right? This is the alpha 1 and this is the alpha 2, right? And this is the pi. Right? This is symmetric. I'm saying the waveform is symmetric as this. Here just I put it 2 alpha, right? One here and one here. I could have another one, right? Another. Keep going. You can go up to whatever you want. Not infinite, but you can go as many as notch you want, you know. So if you do this one, the output voltage, let's say this is a VAO. Right? For example, like a single phase inverter. VAO is going to be, and let's say this is a VDC. Let's say this is VS or VS. VAO is going to be 4 VDC over pi. Is it A sigma n from n to whatever sine n omega t. Well, let's say how much is the an? An is equal to 4 Vs over n pi times 1 minus 2 cosine of alpha 1 plus 2 cosine of alpha 2. So for this case we are done because we have alpha 1 and alpha 2, right? For this case we have only 2. So basically the fundamental harmonic is going to be how much? It's going to be 4 Vs over pi, right? N is 1 for the fundamental. 1 minus, and I'll put that n here. Should be n alpha 1 and n alpha 2. So the V1 or A1, you know, we call it here A1, is going to be 4 VDC. I'm really long. 4 DC over pi times 1 minus 2 cosine of alpha 1 plus 2 cosine of alpha 2, right? But if we have more notch, you know, general equation. General equation is AN is 4 VDC over N 1 minus 2 cosine of alpha 1 plus 2 cosine of N alpha 1. 2 cosine of N alpha 2 minus 2 cosine of N alpha 3 plus 2 cosine of N alpha 4 and so on. So if you have more notches, you know what I'm saying? For example, let's say if you have another one here, look at here, if you have another one here, right? So basically this is the alpha 3, right? And this is the alpha 4, right?
Is there any reason why you take away the pi and the
I can take it away, no, it should be there. It should be there. It should be there. Yeah, and that one is for only one notch, I put it here. But if you have an infinite notch, not infinite, I don't know, whatever number of notches, you can go use that. Yes.
What exactly is the notch referred to?
Notch is this one, this is a notch. Okay, here, we call it notch. For example, if they say, maybe you hear this term, maybe if you go to power system, they call it voltage notch, or they call it voltage sag, you know. Voltage notch is like this. Usually you expect to see a voltage like this, right? I don't know, something crazy happens, suddenly you see something like this. They call it voltage notch. You have a notch. Here they call it notch. And see here, I have one notch here, right? I could have more, I could have something like this. And let's say this is a quarter cycle, and after that is going to happen. Here I have an alpha 1 here, right? Alpha 2 here, alpha 3 here, and alpha 4 here, right? These are two notches, you know. You have an alpha 1 and alpha 2, so you can only select these two such that, I don't know, harmonic 3 will be 0, or 5 will be 0, or I don't know, the fundamental will be this much. But if you have 10 notches, you can go up to harmonic, I don't know, 11, 15, something like that, to cancel them, you know what I'm saying? So basically having more notch is going to give you more control to control the output voltage, to become better sine waveform. But what is the problem with the more notch?
switch?
Every notch means to switch, right? Every notch, boom, coming here and going back there. This is like a bipolar switching, right? They're going from VDC to minus VDC. How about if the waveform is like a unipolar? If the unipolar is going to be like this. If the waveform is like a unipolar, it's going to be like this. Should be symmetrical. Okay, this is a pi over 2, this is a pi, and what is going to happen here? This one is going to copy here upside down, right? Upside down, it's going to be like this. Why we call this one unipolar? Why?
Because it's 0 instead of negative VDC.
Yeah, we have extreme level of voltage, right? This is 2 pi. So what is going to happen to the Fourier series in this case? The if we have that one, this one is all gone. This one is going to be gone. Because we have a 1 minus, 1 minus, 1 minus. So I'm saying those ones, they are gone. for this one, AN is gonna be sorry, say that one is wrong. It's gonna be cosine of n alpha 1 minus plus cosine of n alpha the 2 is gone. Sorry, the 2 is gone. This one does not. The 2 will be gone.
Should there be an N percent higher than that?
Oh, you want me to put the n period? That's the difference in this case. I plot it a little bit different here, you know. Actually, if I'm going to plot it like this, let me correct that a little. Yeah, let me do it this way. The axis is here. Because it should be like that one. And so this is the plot. I'm going to erase the red here. This is the pi, and you repeat it here. Now this is the alpha 1. This is the alpha 2. This is the alpha 3. And this is the alpha 4. We can plot it that way, but the Fourier series is going to be different. Because to match this one, we should start like this. This is for bipolar, you know. So basically, for example, they give you, hey, I want to eliminate, for example, I have a 3-phase converter. If I have a 3-phase converter, do I have to be worried about the third harmonics or not?
No.
Third harmonic already is gone by itself, right? So you are not going to be worried about if I tell you, hey, I want to eliminate the third harmonics and the fifth harmonic, which one do you need? And this much, for example, my fundamental, you know, component. For example, this much V1 I want. So basically, I say, okay, 2 notches is enough, right? Third by itself is gone. I don't need to do anything for the third one to delete it, right? So if I want to delete the fifth, I said here, A5 should be 0, right? And how many notches I had? I had 2 notches, right? So basically this equation stopped here, right? This equation stopped here. We said 4 VDC over 5n, right? Times 1 minus 2 cosine of 5 alpha 1 plus 2 cosine of 5 alpha 2 should be 0, right? Because I wanted to get the harmonic number 5, right? Sorry, I'm going to do the opposite. 5, right? N is 5. Now, for example, I say I want to have this much, for example, fundamental harmonic. I know 100 volts, for example, fundamental harmonics, right? So what does it mean? Means the A1 should be 100. This one is maximum because if I say 100 volt maximum, A1 should be 100. If I say 100 volt RMS, so A1 should be 100 volt times 100 square root of 2, right? Let's say we want to have a fundamental maximum harmonic 100 volt, right? So the other equation is here. We want to A1 would be 100 volt, right? That's what we are saying. So basically, you put it here again. Say 4 VDC over pi because it's a fundamental, right? Times 1 minus 2 cosine of alpha 1. N is 1, right? Because it's a fundamental. Plus 2 cosine of alpha 2 should be 100. Right? VDC is given, for example, 100 volt, 200 volt, whatever it is. Now basically, if you go solve these two nonlinear equations, you will figure out alpha 1 and alpha 2. If you select alpha 1, alpha 2 like that, with, for example, 200 volt given DC bus, right? You are going to have, I don't know, no third harmonics is not there because it's three phase. No harmonic number 5, right? Because we set that one to be 0, and for example 100 would for the first harmonic. If it's a single phase, you could have a third harmonics, but if it's a three phase, you don't have to be worried about the third harmonics. Understand? Yeah. So that's the way to work with harmonics. I'll give you one problem in homework number 2. You can practice it a little bit at home because this equation is going to be solved. Because this is a non-linear equation. You guys think that this is 5, this is the alpha 1, this is 5 alpha 1. It's not easy to solve it. It's going to take time to solve this equation. To make it easy, you know what we can do here, for example, if we are going to do today's exam, because we are not going to give you that kind of. No way you can do it. Yeah, it's lots of calculation, no way we can do it. So this is a harmonic elimination, we talked about it. The next topic we have, we want to talk about the reference frame. Make sure I'm going to go there. Yeah, I think the reference frame, before we start the reference frame, I need to explain it to you what we are going to do, because very possible you're going to get confused. We need to. Yeah.
In the unipolar case,
Yeah.
you still have negative waveforms, right? You just chose to erase them? Or
No, for unipolar,
it's always going to be positive?
it's going to be positive, negative. So this one is going to copy here upside down.
Okay.
I didn't draw that part.
Oh,
Yeah, you should do exactly this one here, but upside down. That's the other part. I didn't draw that one. Let me make sure I'm. There is one more type of switching. We call it a space vector modulation. I'll talk about that one when we get to the project phase. We'll talk about that when we get there. Now the next part is the reference frame code. Before we go there, let me tell you what is this topic we're going to talk about, before we get to the math. Have you heard about the PI controller? Have you heard the term of PI controller? P is the proportional, I is the integral, right? But in general, let's put it this way. Let's put it this way. I have a DC circuit. This is important to understand before we start this topic, why we are doing all this crap for the next month. Just to know why we are doing this.
Is this a PI and PID different, or is that?
The PID has a differentiator also, but let's say, I want to come up with the example, like room temperature, for example, right? We want to put the thermostat somewhere to control this room temperature, for example, at, I don't know, 25 C or something, right? So basically, if we look at it here, we have a reference. This is my reference, 25 C, right? So what we do with the control system is like this. It's okay, I have a reference value. This is, for example, T reference, right? And I'll go measure my actual temperature. I'll put the sensor somewhere, I'll measure the temperature of this room. This is the T actual, right? So the difference between these two is going to give me what? Sorry. This one is going to be error, right? This is error. Now you use a kind of controller. I'm not going to talk about what kind of controller we're going to use, but you use a kind of controller. The simplest one is a PI, or it could be bang controller. We'll talk about that one a little bit later. Or or hysteresis controller. They call it bang bang or hysteresis controller. I'll tell you what that. Now you have this controller, but look at here, this error. What you're going to see here is going to be kind of, this temperature is, this T ref is constant, and this T is going to be, for example, like this. It's going to be like this, right? It's not going to change even this much fast. I'm changing. It's a DC value. My point is the actual temperature is a DC value, right? So this is one system. Keep in mind, you need to design a controller to control this one to be all the time this one, right? Now let's go to the AC waveform. I want to design a system, I don't know what that, I have a reference value, this is for, could be my voltage, could be my current. I want to have this volt, this is my reference. I want to have, for example, I want to build an inverter to give me 110 volt output voltage, fixed. This is the inverter, right? We want to use that UPS. So 110 volt means how much? Means 110 square root of 2 and 110 and with a frequency of 60 Hz, right? This is my reference, right? I want to have something like this. Now, you want to control this output voltage of this inverter, for example, something like this, right? Think about this one. Which one is easier? This one is easier to control it or that?
The first one?
Why? See, there is two parts here. One part is this thing, right? The other part is this guy is going up and down by my reference is changing, you know what I'm saying? My reference by itself is changing, But here, no, my reference is fixed. Just I need to take care of these changes, right? Now, the reference frame theory, what it's going to do? It's going to take this signal to a new frame. You go plot this one, you go simulate this one. To give me, so let me put it this way. Now, instead of regulating the instantaneous output voltage, can I say, hey, I want to have this much RMS value, 110 is RMS value, right? 110 RMS value. If I can control my output voltage to have the same RMS value, for example, like this, right? This one is my reference and that one is my actual value, right? So if I can keep the frequency fixed, 60 Hz, and I can do this one, it's going to end up the same thing, right? But this is much easier because at least I don't have to deal with this, fluctuation of my reference, right? The reference theory is going to take this parameter, how it's going to be done. Let's give you another example. Let's say there is a car moving, right? And there is an object here, and now you are standing here, and somehow you want to keep, you have a flag, you can run, for example, with the car. Let's think about it, You can run with the car with the same speed of the car. You want to keep this flag all the time to be 1 meter from this guy sitting here. 1 meter distance, right? Now, you have to tune two things here. What? First, you should tune your speed with the car, right? Because the car is moving, you have to follow the car, right? The other thing is if this guy moves inside the car, you have to change your hand. You have a foot and hand, right? Foot should go and match with the speed of the car, right? And the hand is going to go match with the movement of this guy sitting in the car, right? Two things you have to do at the same time. Now, think about it. If you are sitting in the car with this guy, right? You're both moving with the same speed. You only need to move your hand, right? Because the running part is gone because you are moving together, right? Reference frame theory. We call it mapping also. You're going to get this 60 Hz component, take it to a new system, which is running with 60 Hz, right? Look at here. This is the waveform here. If you are standing here and watching this waveform, what you are going to see? When you look at the waveform here, it's going to come. You are standing here. This waveform is going to move, right? Turn on the scope. Turn on the scope and connect it to the grid voltage, and don't trigger the voltage. What is going to happen? You're going to see a sine waveform moving all the time, right? It's moving all the time. You are standing here, this one is moving, because that one is moving with 60 Hertz. When you trigger it, you are fixing it with something, you know what I'm saying? But the real voltage is moving, right? Now, how about if you can lock yourself here somehow and move with this one? All the time you are going to see this much value, right? All the time you are going to see this value. You're not going to see a variable anymore. You're going to see a constant number. The reference frame theory is going to take all this thing to a new frame, which is going to work with either maximum value of the sinusoidal waveform or the RMS value of the sinusoidal waveform. We work with the maximum value. So basically, you see, you control the maximum value. So that's good, because if you control the maximum value, you can control the RMS value, and the frequency automatically is set. Why? Because you are sitting in the same car, right? Because you are sitting on the same frequency. You know what I'm saying? So you don't have to be worried about this one to do like this. Hey, I'm going to control this peak. If I control this peak, frequency already is controlled because I'm moving with that system. So this is what we are doing. We are going to take everything to the 60 Hertz system or 50 Hertz system. They call it synchronous frame. Synchronous frame because it means you two moving with same speed. You know, you are moving with your parameter with the same speed. My voltage is going fast with 60 Hertz. I'm moving fast with 60 Hertz. So always I'm going to see the same voltage. So reference frame theory, this is very important because I know last year I figured out lots of people, they didn't understand what they are doing. Reference frame theory will transfer all the parameters to a new frame, which all they are could be arbitrary. You know, for induction machine, they use a different reference frame. But usually in this course, we use a synchronous reference frame. Means we transfer everything to either 60 Hertz or 50 Hertz, whatever is the frequency of the system. So all the parameters now, they're going to be like a DC parameter. They're going to deal with something like this. This is the topic we are going to start right now. How to do it? Let's see. How to do the reference frame. Say we have A, this is a three-phase system, right? A, B, and C. Let's call it FA, FB, FC. The reference for this part, if you want, is the chapter 3 of the book. It's called Analysis of Electric Machinery. I'm not sure which book is in the reference book I use. But you can type it in Google. I think that nowadays there is enough free material. You can find it in Google if you want. Type on the Google to find this kind of material. Now, you are familiar with this one, right? This is a ABC system, right? I'm going to transfer all this ABC system, ABC value, to a new coordinate. This new coordinate, I'm going to go this way. I call it B, yeah. I call this one B, and I call this one D axis, Q axis. Now, let me go a little bit back. Maybe you say, okay, how did they come up with this one? You're a genius to come up suddenly with this kind of thing. If you look at they call it direct axis and quadrature axis. If you go back to the old time, if you look at synchronous machine, they are like this. There is a stator. This one started from the electric machinery. This idea started from electric machinery. Now we apply it to all converters. They call it solid pole, you know, induction machine. Sorry, a synchronous machine. This is the rotor of this machine. They call it solid pole because it's not cylindrical. Remember the DC machine and induction machine, they had a cylindrical rotor. But they got this one, they call it direct axis, D axis, and this one is the Q axis. Hopefully, year after next year, we will offer a course in AC machine drive. You know, we'll talk about all this kind of things, how to do this kind. But this idea started from here. There's a electric body here. There's a winding here, right? There's a winding, and there's a flux going like this, right? They call this one quadrature axis. This one is a direct axis. They use this idea for the same thing. They say I have a three-phase system ABC. I have a D axis, Q axis, and these two, they are perpendicular. These two, they are perpendicular, right? Now, let's say this one is moving with the speed of omega. See, this is the important part. I'm rotating this one with the same frequency I want, right? This one is rotating with the speed of omega. This angle, theta, is going to be omega t plus delta. What's delta? Delta is the initial angle, you know, before this thing starts to rotate. We cannot say it for the grid, those kind, but for electric machine, let's think about the electric machine. If this machine is off, this one is the standing somewhere, right? There is the A axis here also, this is the A axis. They call this one delta, delta 0 or delta. The initial angle, you know, before the machine starts to rotate, is coming from there, you know. But simply here, they have an angle of delta, theta, between the A axis and D axis, right? Now, I want to find the relation between this FA, FB, FC, and FD, FQ. I want to see if I have FA, FB, FC, how I can calculate FD, FQ. Let's see. Let's start with FD. If FA, FB, FC, they are given, can you tell me how much is the FD? FA what? Say. What did you say? Say. Is FA cosine theta, right? You project this one here, right? That's one component. What else?
FB sine.
This is the FD, right? How much is this angle?
120.
One. And how much is this angle? 1. How much is this angle? So how much is the projection of FP on FD? Yeah. Cosine of this angle, right? That's a projection. Whatever is this angle times cosine of that angle, right? How about the FC? Hmm? Right? Because the angle I'm playing to be of 120, right? I'm going to change this one to this one. Does it matter? Hmm? Well, to 120 minus theta, I made it theta minus 120. Because I want to be like a three-phase system. 0, minus 120, and 2. Right? Let's go calculate FQ. Let's go calculate FQ. How much is FQ? How much is this angle? 90 minus theta. So it's going to be FQ cosine of 90 minus theta, right? FQ is going to be FA cosine of 90 minus theta. How much is the cosine of 90 minus theta?
Sine.
Sine. Right? It's sine. Let's go to FB. How much is the FB? Let me see. This is somewhat related to, is this angle plus this angle, right?
120 minus theta
Yes.
plus 90.
I'm trying to see. I can write it mathematics, because I want to think about how I can project it here. We're gonna go all the way this way, say 120 minus theta plus 90, right? Let's write it down, right? How much is this angle? This is the 180 minus 120 minus theta, right? And from here to here is how much? 90, right? So I write it this way. It's gonna be plus FB cosine of how much? 90 plus,
180 minus theta.
yeah, 120 minus theta. Is it correct?
Yeah.
Is it correct? So I say this angle, right, plus this angle.
Yeah.
Right? So cosine of that. Now let's simplify this one. So this one is going to be how much? 90 plus something. It's going to be minus sign, right? It's going to be minus sine of 120 minus theta, right? And this one again I can simplify. How much is it? Theta minus 120, right? So you can guess what's the last one. Or without calculation you can guess it.
Sine of theta plus 120.
FC sine theta plus sine theta. But let's figure it out to see is it or not. Plus. Let's come here. You want to find this angle. How much is this angle? This one is 120, right? This is 120. Yeah, this is 120 plus theta up to here, right? If you go from here to here, is 120 plus theta, right? How much we should subtract? 90, right? So basically this one is 120 plus theta minus 90, right? So this is 120 here, right? This is 120 plus theta up to this FD, right? So I have to go back 90 degree, right? Minus 90. Let's put it there, see how much it's going to be. Yeah. So it's going to be plus FC cosine of 120. Let's put it this way. Yeah, 120 plus theta minus 90, right? We can write this, so we can say, okay, this is the cosine of 90 minus 120 plus theta, right? You can put it this way, right? Is it correct? So how much is this one?
Sine theta.
Sine theta plus 120, right? Any question, guys? Everybody follow this one, what you said here? Yeah. Now, we define a third component, we call it FO, or zero component. FO could be any number. For example, what I here that I selected is 1 over the square root of 2. Oh, I forgot the big thing. Everything times the K. Keep the K, I'll tell you why we are saying. Based on that relation, K is 1, right? What we did here. But I'll tell you how much is the K. Put here, times K. I want to select my zero component. I'm going to select it this way. FO is going to be 1 over the square root of 2 FA plus 1 over the square root of 2 FB plus 1 over the square root of 2 FC. You know, the system is symmetrical. How much is the FA plus FP plus FC? 0 for it. So it doesn't matter. I put the 1 square root of 2 in front of all of them. I'll tell you why I selected this way. I'll tell you later why I put the 1 over square root of 2. Again, this one times K. I call this one zero component. Basically, zero component in a system, it shows you how much your system is unbalanced. You know what I'm saying? If zero component is zero, means your system is perfectly balanced. But if it's not zero, there is something over there you have to work on. Now this K. There are different ways to define this K value. Some people, they work, we are working on a three-phase system. And we are going to another two-phase. O is not something, normally O is zero. We are going from a three-phase system to two-phase system. You look at different books, you see different K value, because some people, they say, they go with this concept. They said, I have this ABC system here. I'm coming to this DQ system. I want to keep my power constant. You know what I'm saying? If I had 1 kilowatt here, I want to have 1 kilowatt here in this system. That's one way to go. The other way to go, some people, they say, these are all going back to the concept of electric machine and those kind of things. Some people, they say, no, I want to keep my phase constant. See, here I had 3 phases, right? Here I had 3 phases, here I have 2 phases, right? Some people, they say, no, I want to go, if I'm going to go 3 phase to 2 phase, I'm going to lose my phase power. You know, for example, in this side, the phase power is going to be 1.5 times of phase power here. You know what I'm saying? Let's give an example. For example, in ABC, we had 3 kilowatt, right? If I go and per phase, I have how much? 1 kilowatt, right? If I go with a constant power, total power, in DQ, right? This is the ABC. This is the DQ, right? This is it. How much is the per phase power here? 1 kilowatt, right? Because I have 3 phase, 1 kilowatt. How much is the per phase here? 1.5. Some people, they go with this. They say, hey, I'm going to keep my total power constant, right? Some people, no, I want to keep my phase power constant. They say, hey, I had a 1 kilowatt here. I want to have 1 kilowatt here, right? So here, 3 phase, how much I'm going to have? 3 kilowatt. Here, how much I'm going to have? 2 kilowatt, right? You can see there's a coefficient of 2 over 3. 2 over 3. Based on which way you go. You know, I think these are all coefficients. You should correct for them at the end to make sure everything is correct. For example, if you go with this one, you should use for the phase power, you should use a 3 over 2. For that one, you should use a 2 over 3. You get the same phase power. Yep. Somebody had a question.
What is the difference? Let's say
There is no difference. It's just I'm saying mapping. How should I say? Mapping a parameter from one system to another system. I'm saying you can go either based on a single phase or 3 phase power. You know what I'm saying? So now I'm going to go back to this K value. I'm going to go back to this K value. Going back to this K value, I call my matrix C. I'll say, I'm going to make it simple. I said F, actually I should have put it this way, F D Q O is equal to C. C is a matrix, times F A B C. F D Q O is F of D, F of Q, F of O. Just I'm putting F general name. Later on, we're going to use the voltage and current. VDV, VDV, QVO, AD, ADAQAO. ID, IQ, IO. And F of ABC is FA, FB, FC. Right? Now, I want to see what's in matrix C. C is going to be, I leave a little bit of space here. So I'm going to go with that one. It's going to be cosine theta minus 120, and cosine theta plus 100. Sine theta minus 120, sine theta plus 120. And 1 over the square root of 2, 1 over the square root of 2, 1 over the square root of 2. Now there's a K factor here. I'm going to select K to be 2 over 3. couldn't remember it exactly. But this is, I think, is based on the total power, to keep the total power constant, going from the ABC to the DQ, 3 kilowatt to 3 kilowatt. These 2/3 is selected based on that. This is a matrix we are going to use it a lot for future. Why I selected this square root of 2 and this one this way, because if you calculate C minus, that's kind of pain to calculate the inverse matrix of this one. But selecting this 1 over square root of 2 is going to make it really simple. And C minus is going to be 2/3, sorry, 3/2. C transpose. Check this one, at home, to make sure it's correct. Check it, to make sure it's correct. You transpose this one, right, with the 2/3 times this. Yeah.
Actually, this two-phase system.
You're making one small mistake. Check, somebody check, guys, check this one at home. This will be, because I think this small thing, let me quickly check something. It's going to be C transpose. This one is going to be here. I'll check it myself at home. Just I want to make sure I didn't miss anything here. But this is a C minus. Why we need the C minus? Because now if I need my ABC, FABC, right? FDQ. So usually it's like this. We are in the US, we have $1 money. We are going to go to Mexico, buy something, right? They like dollar or whatever than I don't know, peso, I'm not sure what they're doing this. But normally you should do this. You should go convert the money to peso, buy whatever you want, sell it, for example, again, convert it back to US when you're coming $2, right, when you're coming back here. This is exactly what we are doing. For the control purposes, we are going to go convert the ABC to DQ. We'll do all the control things we want to do. When we are done, we should come back to the real life. DQ is a math concept. There is no circuit like that, no real converter there, you know what I'm saying? You convert everything to this new frame, to this new system. You do all your calculation, your control things. At the end, you calculate those switching patterns, you know what I'm saying? What is coming out from your DSP, from your controller, is a switching pattern to tell this switch is turn on, turn off, turn on, turn off, right? To get that one, you have to go back to the ABC system. So basically, we need a C minus here. Any question? I want to calculate the power equation before we go today. Any question? Now, let's use this, what we said here, one example. I want to calculate the power in a system. See how we can calculate power in a system. If I have a three-phase system, how much is the active power? How much is the power? Not the active power, power. It's going to be VA, IA, three-phase system power calculation. Active and reactive power calculation. If you want to put a title for it, active and reactive power calculation, three-phase system. P is the VAIA plus VBIB plus VCIC. Is correct? You have a three-phase, and each phase has the power. VAIA, VBIB, right? Equal. I'm going to put this one. I'm going to say this one is VA, VB, VC times IA, IB. I selected it correctly. This one times this is a 1 by 3 times 3 by 1 is going to be 1 by 1, right? So basically, this one is a VABC transpose. Am I right? Go with this concept. Look at here. FABC was like this, right? If it is horizontal, it should be transpose of that, right? So this is a VABC transpose. And what is this one? IABC, right? So basically, IABC is this. IA, IB, IC, and VABC also is VA, VB, VC, right? I want to calculate my active and reactive power within DQ system. I know in ABCC system is like this. I want to calculate them with DQ system. Let's write it down. So P is equal to that, right? I have a VABC. Let me summarize what I said here. Let me summarize it here. Here what we got here, we said F DQO is C FABC, right? That's what we have. And FABC is C minus FDQO, right? This is what we have. Now, if I want to calculate if I want to replace this one, how much is the VABC transpose? I'm going to write VABC transpose. I'll put it this way. I can put it this way, right? Now I can say VA. How much is the VABC? Look at that equation to it. It's going to be C VDQO, right? Correct or not? Can you see it here?
C or
No. How much is the VDQO? C VABC, right? C, but be careful. They should be like this, the matrices. That's the reason I put the transpose out, right? So basically, it's going to be this one. It's going to be C VDQO transpose, right? It's the VABC. Huh?
C inverse.
Oh, I'm wrong. You're right. Here I'm going. Yeah, C minus. You're right. C minus VDQ. You're right. Sorry, VDQ. C minus VDQ. Times. How much is the IABC? How much is the IABC? IDQ. Right? If we have an AB transpose, what is the result? Now you start to know what was the linear algebra with the power electronics. Now you need to know a little bit linear algebra, you know? So AB transpose is a B transpose A transpose, right? So this one is going to be VDQO transpose, right? Times C minus transpose, right? Times C minus, right? Times IDQ. Now, let's come here. Let's come here. I'm going to replace C minus 1, C inverse, with a 3/2 C transpose. Can I do that? So I'm going to replace this one. Okay? Look at it. Because I'm going to write here. Instead of C minus, I'm going to put 3/2 C transpose, right? Transpose. There's one more transpose here, right? How much is this one? Transpose. You know what's transpose, right? Transpose, you just move all the rows is going to be common, right? This row is going to come here, this row is going to come here, and the third row is going to be third column, right? So if you transpose 2 times, what's going to happen? Nothing, right? Nothing. You put this one from here, and you put that one from here, here. So basically, you didn't do anything, right? So this is the how much? And the 3/2 transpose is what? 3/2. There is no transpose, right? Now, let's replace it here. So P is going to be VDQO transpose, right? Times. How much was this one? 3 over 2c times. This one is c minus, right? C minus times IDQO. 3 over 2 can come here, is that 3 2 VDQO transpose times C times C minus, how much is it? No, it's not 1, it's I3. Right, it's I3 by 3, right? What is like 1? When you have matrices, it's like 1, you know? So basically, now this one times this, how much is it? I3 by 3 times IDQO? IDQO, right? So basically it's going to be now let's write that. So it's going to be 3 over 2. VDQO transpose is going to be like VD, DQ, DO, right? Times ID, IQ, IO. So basically P is going to be 3 over 2. VD, ID, VD, ID plus VQ, IQ plus VO, IO. In a balanced system, VOIO, basically all of the values there, VO is 0, IO is 0, all they are 0. So basically P is equal to
So in unbalanced system, that becomes a free phase.
still is DC value, you know. You're not going to see the unbalanced system in this class. But when you simulate this one, you know, you do some homework, just put a little bit of balance to create it, you can see what you're going to see, you know, when you're doing the simulation. If you're curious, you know, when you get there, make it a little bit unbalanced to see what you're going to see for whole value. You know, but usually systems are balanced. Now we calculated P. Right? I want to go calculate Q now. I want to go calculate Q. I want to go calculate Q, just want to see. Let's put this one here. How do we define these cases? This is my D-axis. This is my Q-axis. I need to calculate the reactive power. I put my D-axis, Q-axis from the frame I had here. I put it here. Now I want to put my current and voltage vectors here. In general, it could be anything, but either VAIA or VBIB or VCIC. Usually we go with the VAIA. The first place. So if this is a V in general, if this is the I, this is the power factor, right? Cosine of this one is the power factor. Cosine of phi is the power factor. Let's call this one Ci, phase of current. Let's call this one Cv, phase of voltage, right? So if you project this one here, this is the IQ, right? If you project this one here, this is ID. If you project this one here, is the VD. And if you project this one here, this is the VQ, right? And in general, What's the relation between the P and Q? If this is a P, this is a Q.
Sine and cosine.
Tangent phi is equal to Q over P, right? Tangent phi is Q over P, right? TAN phi is equal to P, Q over P. Or Q is equal to P tan phi, right? Tan phi. So what is phi here? There is an easy way to prove it. You know, I want to first go through the painful way. Phi, how much is the phi? Phi is phi v minus phi I, right? Phi v minus phi I, right? So, how about tan phi? It was tan phi v, tan phi I, sorry, minus tan phi I 1 plus tan phi v tan phi I, right? Let's calculate this thing. I'm putting it here. So tan phi, I'll go directly calculate Q. Q is going to be P. How much is the P? Is 3 over 2 Vd Id plus Vq Iq times, now we'll go over. How about tangent phi? Phi v. This is phi v. It's going to be this one, right? Divided by this one. It's going to be Vd over Vq, right? Tangent phi v is going to be Vd over Vq. How about tangent phi r? Id over Iq, right? Yeah, simplify this one. So this one, the Vd Vq plus Vd Iq plus Vd Id divided by Vq Iq, right? That part is going to cancel with this. And if you time this one here, Q is going to be 3 over 2 Vd Iq minus that one was the power. That one was the power. That one, this one is the reactive power. One easy way, let's say it quickly, one easy way. I'm going to just look at this value. Q. I'm going to say it another way. This 3 over 2 is going to be here, but this term. Look at it here. I have a voltage, I have two voltages, Vd and Vq, and two current, Id, Iq, right? Let's say how much reactive power they're going to generate. Vd and Id, how much reactive power they're going to generate? Why? They are in phase. How about Vq, Iq? How much? Zero. Now, how about, so two of them, they are gone, right? So, how about Vd, Iq? How much reactive power? Vd, Iq, positive or negative? Sine 90 is 9. No, but I'm saying positive or negative. So, let's go to the next. How about the VQ ID? Why negative? Current is leading, right? Here, if you look at the Vd IQ, the voltage is leading 90 degrees positive. Here, the current is leading negative. Put that over there. Vd IQ minus VQ ID. So easily you can calculate it. You don't have to go through this tangent, those kind of things to calculate. The last thing for today. Now, I want to make my life a little bit easier. What I'm going to do, I'm going to select this Q axis. Let me make sure I get it. I want to select this Q axis to be, this is arbitrary, where I'm going to put them. to rotate them with omega is not arbitrary. I have to rotate with 60 hertz, 50 hertz, right? But where I'm going to put it, see, I put the A, B, C here, right? A, B, C, right? I'm going to put it, I can put it here, right? I can put Q axis here, or I can put the Q axis here, or here, right? If I line up my Q axis with my voltage, VA, it's going to be like this. If I select the Q axis like this, this is the Q, this is the V, this is the I, and this is the ID. So, sorry, this is the D. What is going to happen? How much is the V? D. How much is the VQ? This is the value I'm saying. Whatever V is here, VQ is going to be that much, right? So what is going to result here? Just replace them here. VD is 0, right? So P is going to be 3/2 VIQ. Because VQ is V, right? Here, again VD is 0. This term is gone, right? It's going to be how much? VI. What is V? Amplitude of the voltage. See, this is the ABC voltage, right? Whatever, either you select the RMS or maximum. That's that voltage, right? Maximum of that voltage, right? Or RMS of that voltage. What does it mean here? This is constant. I'm connected to a grid. It's 120 volts, 480 volts, something like that, right? 480. I can control active power with IQ, right? If I control my IQ, I'm controlling my active power. If I control my ID, I'm controlling my reactive power. So keep it here, now we go from here. Actually, I have to go back to that here to please move it. I have to go now. I cannot wait. So have this one here. We got the P and Q equation for a three-phase system in the DQ system. And we'll start with the diagram next class. Guys, I have to go today. I cannot go. But one person had a question. He sent me an email from somebody. What the minus V control. So just quickly to answer that one. You use this one for the bipolar, right? If you use this one, right? This one is for leg A. For leg A, you use this one. For leg B, you are not going to use this one anymore. He had a question. He sent me an email just to explain it to him. And for leg B, you use this to compare it with square. That's the difference. That's what it is.
And there's no class on Tuesday, right?